Hello, my wonderful chemists. Today we're going to start chapter 7 and 8, which discuss bonding. Chapter 7 is mostly about ionic and metallic bonding, and chapter 8 is covalent bonding. So as always, we have our poem here at the beginning of our packet. Then we have our learning targets. Make sure that you are checking those at the end of the chapter. And we're going to start with a little brief overview of the differences between the three types of bonding: ionic, metallic, and covalent. After that, we're going to spend a little bit of time on ionic, a little bit of time on metallic, and the rest of the time we're going to spend discussing covalent. So first, why do atoms bond together? Well, the reason why they bond together is to achieve a low energy configuration. So nature prefers having low energy, and so noble gases, for example, that are not very reactive, they have pretty low energy. They have a stable electron configuration. All their sublevels are filled, and so that gives them a lower amount of energy, and they are more stable. So the other atoms try to achieve that low energy configuration, and that's why they try to react so that they have an electron configuration similar to those noble gases that are stable. So basically they do that by achieving a noble gas configuration. All right, so let's compare between the three types of bonding in terms of all of different things, and we're going to start with the atoms involved. So with ionic bonding, from its name, it's made up of ions, and it is made up of a metal cation and a non-metal anion. So you have a metal bonding with a non-metal. Covalent is between two or more nonmetals. So an example of ionic is like NaCl or calcium fluoride, or any compound that's made up of metal and nonmetal. Covalent would be two or more nonmetals, so for example, water, carbon dioxide, sulfuric acid. So all nonmetals involved. Metallic bonding might be new to you. Metallic bonding occurs between atoms of the same metal. So for example, let's say I have a piece of copper, and so the copper atoms are all bonded together metallically. So examples of metallic bonding, you could pick any metal that's on the periodic table and list that as an example. So copper, sodium, potassium, cobalt, gold, iron, any of the metals on the periodic table. So the main difference here is, what they do with their electrons. So chemistry, bonding happens when electrons are transferred or shared. And so it's really important to understand what happens with electrons. So in an ionic bond, when a metal and a nonmetal bond together, we have giving and taking of electrons. So the metal loses electrons, the nonmetal gains the electrons. And the reason for that is, if you remember, metals on the periodic table are to the left side, and they typically have like one or two valence electrons, just a few, and so it is much easier, requires less energy to lose one or two to become like noble gases than it is to gain 6 or 7, a whole bunch. And so metals tend to lose electrons, like we learned in the last chapter. Nonmetals are the opposite. They have a lot of valence electrons. Most of them have like 5 or 6 or 7, and so it's much easier to gain a couple of electrons than it is to lose a whole bunch to become like noble gases. So metals want to lose their electrons, nonmetals want to gain electrons. So that's perfect. When you put a metal with a nonmetal, the metal will get rid of its electrons to become stable. The nonmetal will gain those electrons to become stable. And so when you lose and gain electrons, you have ions forming. So the metals become positively charged, they become cations, and the nonmetals gain the electrons to become anions, negatively charged. And that's why it's called ionic bonding, is because it's made up of ions, positive and negative charges, because you're losing gain electrons. And so what holds an ionic substance together? Why, like for example, in NaCl, NaCl is really made up of ions. It's made up of Na plus and Cl minus. So why does the Na plus and the Cl minus stay together? What is the bond that is holding those together? Well, because one is positive and one is negative, those attract, and that's what holds NaCl together, or any ionic salt together. So we call these positive and negative attractions either electrostatic attractions or Coulombic attractions. So let's write that down. Electrostatic or Coulombic. You don't have to say both, just pick one. Attractions. What that means is positive and negative. And those attractions are between the metal cations, because they're positive, and the non-metal anions, because they're negative. Okay, let's look at covalent and what happens with electrons. Well, covalent is between nonmetals, all nonmetals, right? So nonmetals want to gain electrons. So let's look at water, for example. Hydrogen and oxygen both want to gain electrons. So what do? Well, they have to learn to share. So they end up sharing their electrons. And so what holds them together? What holds the oxygen to the hydrogen and water, for example? It's because they are sharing an electron cloud. So when they have an electron cloud shared, that keeps those two atoms or two nuclei together. Now let's talk about metallic bonding. That might be new to you. So if you take, let's say, a piece of copper, and it's made up of a bunch of copper atoms, well, all these copper atoms are trying to lose their valence electrons, right, to become stable. So I'm going to use M for metal. Let's say the first atom loses an electron and becomes a cation to make it stable. The next metal atom also loses an electron to become stable, and the next one, and the next one, and so on. Well, if there's a non-metal around, you'd have an ionic bond, right? The metals would lose their electrons, but then the non-metal there gains the electrons. Well, if there's no non-metal around, what's going to happen? Well, all these metal atoms lose their electrons, but the electrons have nowhere to go. So the electrons kind of like float around, trying to go from one cation to the next, but nobody really wants them. And so we say we have metal cations in a sea of delocalized electrons. Delocalized electrons. What does that mean? Delocalized means they don't have a locality, they don't have a certain spot that they should be in. Those electrons are delocalized, they're moving around everywhere. So they are moving around from one cation to the other, but nobody really wants them. So what holds this together? Well, the electrons are negative, the cations are positive, so again, there's a Coulombic attraction, positive and negative attraction, between the cations and the electrons. Coulombic attraction between the positive cations and the negative electrons. So I think of bonding as an analogy, as like food. So ionic bonding would be like, I'm with a friend, I have lots of food and I'm not hungry. My friend doesn't have much food and she's really hungry. So I say, well, I'm trying to get rid of this food. I'm not really hungry. So I'm going to give it to you. And she takes it because she's hungry and she didn't have any. So that would be like ionic bonding. We're giving and taking. One has extra, they don't need it, and so they give it away. And the other one wants it, and so it takes it. So giving and taking of electrons. Covalent bonding would be like going to a potluck. We're all hungry. We all bring our food, And we all put it on the table and we all share and we all eat. So that way we all benefit from all the different kinds of food. And so same idea here, all the non-metals want those extra electrons, so they all learn to share their electrons. With metallic bonding, it's kind of like going to a potluck, but nobody's hungry. So everybody brings their food and says, here, take my food, have some food, I don't want it. And the next person says, here, take this food, I don't want it. And so everybody at the potluck party puts their food on the table there and says, please take my food, I don't want it, I'm not hungry. But then the food just sits there, nobody's hungry and nobody eats it. So that's what metallic bonding is like. All right, let's talk about melting points. So ionic substances have very, very high melting points. We're going to say very high melting points. Have you ever tried to melt salt at home? It's not easy. You require thousands of degrees to get it to melt. So very, very high melting points relatively. How about covalent substances? Have you ever tried to melt water? It's already melted, right? You ever tried to melt carbon dioxide? Well, it's already melted and vaporized. How about sugar? Well, it's pretty easy to melt, right? If you heat up sugar, it melts and then, burns. How about wax? Pretty easy to melt again. So pretty low melting points. With metals, have you ever tried to melt a metal before? Well, maybe. Maybe you've soldered before. So some metals have, relatively low melting points, but most metals have pretty high melting points. So I'm just going to say high. Not as high as ionic, but pretty high compared to covalent. And it all has to do with something called intermolecular forces, which we're going to learn about in this chapter a little bit later. State at room temperature. All ionic substances at room temperature are always solids. And they have very high melting points. They're not just solids, but they are solids that have very high melting points. For metals, most of them are solids. There's one that is not a solid, which is mercury. So solids, except for mercury. It is a liquid. How about covalent? Well, water is a liquid. CO2 is a gas. Wax and sugar are solids. So, we're just going to say variety. They could be solids, liquids, or gases at room temperature. Solubility in water. So let's think about this. Salt. Can you dissolve salt in water? Yes. Now, not all ionic substances are soluble, but most of them are. So we're going to say most are soluble. How about metals? Have you ever tried to dissolve a metal? If I take my gold ring and put it in water, does it dissolve? No. How about copper, lead, iron? Any of your metals dissolve in water? No. So insoluble. They're not soluble. How about covalent? Can you dissolve sugar in water? Yes, you can. How about wax in water? No, you can't. So that one again is a variety. Actually, most are insoluble, but there are some that are soluble. Conductivity. Which one do you know conducts out of these three? Well, we know metals conduct, right? So these conduct as is, as solids. All right? How about ionic? Well, if you were to try to take like a conductivity meter and stick it into like salt, it does not conduct as a solid. But if you were to melt or dissolve an ionic substance in water, it does conduct. So they conduct, but only if they're dissolved or molten. Now let's talk about the reason for that. So let's say you have NaCl. So NaCl is made up of, let's see, where can I draw? I'm just going to draw it on the side here. So NaCl is made up of these Na pluses, Cl minuses, Na pluses, Cl minuses, and there's like a crystal that is made up of these ions, right, as a solid. So they are made up of pluses and minuses, but these pluses and minuses are really compacted into a crystal next to each other, and the net is that it's neutral. Really, any compound, in order for it to exist, is neutral. So NaCl is made up of Na plus, Cl minus, so it ends up being neutral, so it does not conduct. When you get it to melt or dissolve, basically that crystal breaks, and the ions are free to move around. And when the ions are able to move around, you have positives and negatives that are separated. When you have separation of charges, electricity is able to flow. Electricity is the flow of electrons, right? And so electrons will flow if you have positives and negatives separated. And so again, ionic substances will only conduct if they are molten or dissolved, not in the solid form. With metallic bonding, metals will always conduct, whether they're solids, liquids, or gases, because, well, not gases, I guess, but if they're liquids or solids, because you have this sea of electrons, right? And so if you have a sea of electrons, the electrons are already moving around, and so that allows already for the flow of electrons from electricity. So that's why they will always conduct. How about non-metal, how about covalent? Do they conduct? No, they do not. They never conduct. Are non-conductors. So why is it that they tell you, don't, when it's wet outside, hide if there's thunder, or lightning. So why would lightning strike you if you're wet? Or if you're in the shower, they tell you don't use your hair dryer or any electronics when you're in a wet environment. Why is that if water does not conduct? Well, water doesn't. Distilled water, pure water, will not conduct because it's not made up of any ions. It doesn't have any positives or negatives, no way for a flow of electrons, right? The electrons are kind of stuck in their electron cloud. So it does not allow for any conductivity. However, tap water is not pure water. Tap water actually has ions in it. It has fluoride for your teeth. It has chloride to kill bacteria. So tap water actually conducts a little bit because it is made up of ionic substances that are dissolved in water, and so it will conduct slightly. The other reason is your own body produces salts. Have you ever tasted your tears or your sweat? It tastes salty. That's because you have salts or ions in your body. And so you have ions on your skin, you have salts on your skin. So if your skin gets wet, well, guess what? You're making a solution of an ionic substance dissolved in water, which will conduct. So your body will conduct because you have salts, and you add water to that, and then it conducts. But pure water, just H2O, will not conduct electricity. Okay, the smallest unit. So if I have a tiny bit of like copper, a metal, what do I call that? Like the smallest unit of copper? Well, it'll be called an atom of copper. So the smallest unit of metallic substance is an atom. How about water? Covalent. If I have just one tiny thing of water, what do I call that? The smallest unit of water. I call that a molecule. You have a molecule of water, a molecule of CO2. How about ionic? Well, so far we've been calling it a molecule. In some courses, just to simplify things, we call it a molecule. But in reality, the correct name for it is formula unit. Formula unit means the same thing as a molecule. It's the smallest unit of an ionic substance. So molecule and formula unit are kind of the same thing. You call a smallest representative unit of an ionic substance formula units. You call a smallest representative unit of covalent substance a molecule. They kind of mean the same thing, molecule for covalent, formula unit for ionic. Let's define these just so we have them. We just talked about them, but let's write out the definitions. We've talked about chemical formula before. It is a formula that shows the types and number of atoms in the smallest unit of a substance. For example, H2O is a chemical formula, NaCl is a chemical formula, and so on. Formula unit, like we just said, is the smallest representative unit of an ionic substance. For example, I can have 2 formula units of NaCl. A molecule is the smallest representative unit of a covalent substance. So I can have like 3 molecules of water. So, all right, let's play a game. Ionic, metallic, or covalent? So let's look at these. We'll start with NaCl, sodium chloride. Is that ionic, metallic, or covalent? So sodium chloride, we have a metal with a nonmetal, so that would be ionic. Number 2, carbon dioxide. Carbon's a nonmetal, oxygen is a nonmetal as well, so that would be covalent. Copper. Copper is a metal just by itself, so that is metallic. Lithium bromide. Lithium's a metal, bromine is a nonmetal, so that would be ionic. Next one, copper 2 sulfide. Don't let that 2, the Roman numerals, bother you. It doesn't matter. Copper is a metal. Sulfide comes from sulfur, which is a nonmetal, so that would be ionic. Dinitrogen pentoxide. Again, don't let these prefixes intimidate you. Nitrogen is a nonmetal. Oxygen is a nonmetal, so all nonmetals, so that would be covalent. Tungsten. Tungsten is a metal. Do you know where you find tungsten? In light bulbs. There's a tiny thin layer, like coil of tungsten. When you hook it up to electricity, the reason why light bulbs glow and give us light, remember from chapter 5, the electrons absorb the energy from the electricity, get excited, they fall back down, emitting energy, and so that's what tungsten does, very brightly, and so they use it in light bulbs. Cesium hydroxide. Let's see, cesium is a metal. Hydroxide, that doesn't sound familiar, but if you have a metal bonded to something else, it's probably ionic, right? Hydroxide is actually oxygen and hydrogen together, so that would be ionic. Aluminum foil. Well, aluminum foil is just aluminum, so that's metallic. Water, H2O. Hydrogen and oxygen are both nonmetals, so that is covalent. Sugar. This is the formula for sucrose, C12H22O11. That is covalent, all nonmetals. And then finally, sodium is metallic.